Have you ever wondered how a massive aircraft like the Boeing 787 Dreamliner moves so smoothly through the sky? How does a pilot control something that weighs more than 250 tons and still perform precise turns, climbs, and descents? Today, we're going to break down the Boeing 787 flight control system, one of the most advanced fly-by-wire systems ever built. By the end of this video, you'll understand how pilots, computers, and control surfaces work together to keep the Dreamliner flying safely. Flight controls are the systems that allow pilots to control the direction and attitude of the aircraft. Every airplane uses three main axes of movement. First is pitch, the nose moves up or down. Second is roll, the aircraft tilts left or right. Third is yaw, the nose moves left or right. The Boeing 787 controls these movements using advanced fly-by-wire technology, which replaces traditional mechanical linkages with electronic signals. Instead of cables and pulleys, pilot inputs are converted into electrical commands sent to flight control computers. The Boeing 787 uses a fully digital fly-by-wire system. When the pilot moves the control column or rudder pedals, sensors detect the movement. These signals are then sent to multiple flight control computers, which analyze the input and determine the safest and most efficient way to move the aircraft. The system then commands hydraulic actuators to move the control surfaces. This technology improves. It also includes flight envelope protection, preventing pilots from exceeding safe limits like excessive bank angles or dangerous pitch attitudes. The Boeing 787 has three main primary flight control surfaces. Let's break them down. Ailerons. Ailerons are located on the trailing edge of the wings. They control the roll of the aircraft. When the pilot moves the control column left, the left aileron goes up and the right aileron goes down. This creates a difference in lift between the wings, causing the aircraft to roll. Elevators. Elevators are located on the horizontal stabilizer at the tail. They control pitch movement. When elevators move up, the aircraft's nose goes down. When elevators move down, the nose rises. This allows the aircraft to climb or descend. Rudder. The rudder is located on the vertical stabilizer. It controls yaw movement, allowing the aircraft to move its nose left or right. The rudder is particularly important during In addition to the primary controls, the Boeing 787 also uses secondary flight control surfaces. These help improve performance during different phases of flight. Flaps are used during takeoff and landing. They extend from the wings to increase lift and allow the aircraft to fly safely at lower speeds. Spoilers. Spoilers are panels on top of the wings. They serve multiple purposes. Stabilizer trim. The stabilizer trim adjusts the angle of the horizontal stabilizer. This helps balance the aircraft and reduces pilot workload during long flights. Safety is the most important aspect of aircraft design. That's why the Boeing 787 flight control system includes multiple layers of redundancy. The aircraft uses several independent flight control computers. If one computer fails, another immediately takes over. The aircraft also has multiple hydraulic systems and electrical backups to ensure the control surfaces continue operating even during failures. This redundancy ensures the aircraft remains fully controllable in almost any situation. During flight, the pilot inputs commands through the control column and rudder pedals. These commands are processed by the flight control computers, which calculate the required movement of each control surface. The computers then send signals to hydraulic actuators that move the ailerons, elevators, rudder, flaps, and spoilers. All of this happens within milliseconds. The result is a smooth, stable, and highly efficient flight. The Boeing 787 Dreamliner represents a huge leap forward in aviation technology. Its advanced fly-by-wire flight control system makes flying safer, smoother, and more efficient. Understanding how these systems work gives us a deeper appreciation of the incredible engineering behind modern aircraft. If you enjoyed this video, don't forget to like, subscribe, and follow Skyscience-Aircraft for more aviation engineering content.
Most modern aircraft use engine bleed air to power several onboard systems, but the Boeing 787 Dreamliner does something completely different. It is the first large commercial aircraft designed with a bleedless architecture. So the big question is, why did Boeing remove the traditional bleed air system? And how does the aircraft operate systems like air conditioning, anti-ice, and engine start without bleed air? On most aircraft, bleed air is high-pressure air extracted from the compressor stages of the engine. This hot, compressed air is then used to power several aircraft systems, such as aircraft like the Boeing 787 and Airbus A320 rely heavily on bleed air for these functions. However, extracting bleed air from the engine reduces engine efficiency because it steals energy from the engine compressor. Traditional bleed air systems have several disadvantages. First, they reduce engine efficiency and fuel economy. Second, they add complex piping and valves throughout the aircraft. Third, they increase maintenance requirements and system weight. Boeing wanted to design an aircraft that was more fuel efficient, lighter, and easier to maintain. So engineers made a revolutionary decision. Instead of using engine bleed air, they would replace it with electrical systems. The Boeing 787 uses a bleedless architecture, meaning the engines do not supply compressed air to aircraft systems. Instead, the aircraft relies heavily on electric power. The engines drive large electrical generators that produce significantly more electrical power than previous aircraft. This electricity is then used to power systems that previously relied on bleed air. For example, electric compressors supply air for the environmental control system. Electric heaters are used for wing anti-ice. Electric starter generators are used for engine starting. This design dramatically changes how aircraft systems operate. In traditional aircraft, bleed air from the engines is used to power the air conditioning packs. But in the Boeing 787, the environmental control system uses electric compressors instead. Air is taken from outside the aircraft and compressed electrically before being cooled and distributed to the cabin. This system provides passengers on the 787 often notice the cabin feels less dry and more comfortable. Most aircraft use hot bleed air from the engines to heat the wings and prevent ice formation. But on the Boeing 787, wing anti-ice uses electrical heating elements instead. These heaters warm the leading edge of the wing to prevent ice buildup during flight in cold conditions. Using electrical heating removes the need for hot air ducts running from the engines through the wings. This reduces system complexity and improves reliability. In older aircraft, engines are typically started using bleed air from the APU or another engine. The Boeing 787 instead uses electric starter generators. These powerful electric motors spin the engine during startup until it reaches self-sustaining speed. This eliminates the need for complex pneumatic starting systems. The bleedless architecture provides several advantages. First, the engines operate more efficiently because no air is extracted from the compressor. Second, the aircraft has simpler plumbing and fewer valves. Third, maintenance is reduced due to fewer pneumatic components. Overall, the Boeing 787 achieves The Boeing 787 Dreamliner represents a major shift in aircraft system design. By eliminating the traditional bleed air system and replacing it with advanced electrical systems, Boeing created one of the most efficient aircraft in modern aviation. The bleedless architecture improves engine efficiency, reduces complexity, and enhances passenger comfort. It's a perfect example of how modern engineering continues to push the boundaries of aviation technology. If you enjoyed this video, don't forget to like and subscribe to Skyscience-Aircraft for more aircraft engineering explanations. The Boeing 787 Dreamliner is one of the most advanced aircraft ever built. But what makes it truly revolutionary is not just its engines or electronics, it's the aircraft body itself. Unlike traditional airplanes made mostly from aluminum, the Boeing 787 is built primarily using carbon fiber composite materials. But why did Boeing make this dramatic change? And what advantages does carbon fiber give to modern aircraft? Let's explore why the Boeing 787 uses a carbon fiber body. For decades, most commercial aircraft were built using aluminum alloys. Aluminum is strong, lightweight, and relatively easy to manufacture. Aircraft like the Boeing 737, 747, and 777 rely heavily on aluminum structures. However, aluminum has several limitations. Over time, it can develop corrosion and metal fatigue, especially after thousands of flight cycles. This requires frequent inspections and maintenance. Aircraft manufacturers began searching for stronger and lighter materials. This led to the development of advanced composite materials. Carbon fiber is a composite material made from extremely thin strands of carbon. These fibers are woven together and combined with resin to create a very strong and lightweight structure. Compared to aluminum, carbon fiber is stronger, lighter, more resistant to fatigue, more resistant to corrosion. Because of these properties, carbon fiber is widely used in industries like spacecraft, racing cars, and modern aircraft. The Boeing 787 was the first commercial aircraft designed with more than 50% composite materials. One of the biggest advantages of carbon fiber is weight reduction. A lighter aircraft requires less fuel to operate. Since fuel is one of the largest costs for airlines, reducing aircraft weight can save millions of dollars. The Boeing 787's composite structure makes the aircraft significantly lighter compared to similar aluminum aircraft. This contributes to around 20% better fuel efficiency compared to previous generation airplanes. For airlines, this means lower operating costs and reduced carbon emissions. Aluminum aircraft structures can corrode over time due to moisture and environmental exposure. This is especially common in areas exposed to humidity and salt air. Carbon fiber composites are much more resistant to corrosion. For airlines, this improves aircraft reliability and reduces maintenance costs. This means aircraft structures last longer and require less maintenance. Lower maintenance requirements, The use of carbon fiber also allows engineers to design a better passenger cabin environment. Traditional aluminum aircraft are limited in how much cabin pressure and humidity they can safely handle. Carbon fiber structures are stronger and more flexible. This allows the Boeing 787 to maintain lower cabin altitude, higher humidity levels, and better air quality. Passengers often report feeling less tired and less dehydrated after flying on the Dreamliner. This greatly improves long-haul travel comfort. Lower cabin altitude, higher cabin humidity, better passenger comfort. Carbon fiber composites also allow manufacturers to build larger structural sections. Instead of assembling many small aluminum panels, the Boeing 787 fuselage is built in large composite barrel sections. These sections are manufactured in factories and then transported for final assembly. Using large composite sections reduces the number of joints and fasteners. This improves structural strength and reduces potential weak points. It also speeds up aircraft production. Although carbon fiber provides many advantages, it also introduces new engineering challenges. Composite materials require special manufacturing techniques and inspection methods. Damage detection and repair procedures are different compared to metal aircraft structures. Because of this, engineers and maintenance teams had to develop new technologies and training programs to support composite aircraft. Despite these challenges, the benefits of carbon fiber make it the future of aircraft design. The Boeing 787 Dreamliner represents a major breakthrough in aircraft design. By using carbon fiber composites for most of its structure, Boeing created an aircraft that is lighter, more fuel efficient, more resistant to corrosion, more comfortable for passengers. This innovation has influenced the design of many modern aircraft. As aviation technology continues to evolve, composite materials will play an even bigger role in the future of flight. If you enjoyed this video, don't forget to like and subscribe to Skyscience-Aircraft for more aviation engineering explanations.
Modern aircraft are no longer controlled only by cables and pulleys. Instead, they rely on powerful computers that constantly monitor and control the aircraft. The Boeing 787 Dreamliner uses advanced flight control computers that process pilot inputs and automatically adjust control surfaces for safe and efficient flight. In this video, we'll explore how the Boeing 787 flight control computers work and why they are critical for flight safety. Flight control computers are the brains of the aircraft's flight control system. Instead of mechanical linkages connecting the cockpit controls to the wings and tail, the Boeing 787 uses a fly-by-wire system. When the pilot moves the control column or rudder pedals, sensors detect the movement. These signals are sent to the flight control computers, which analyze the input and determine how the control surfaces should move. The computers then send commands to hydraulic actuators that move the aircraft's ailerons, elevators, rudder, and spoilers. Flight control computers. Brain of the aircraft pilot. Input, computer, control, surface movement. The Boeing 787 uses a fully digital, fly-by-wire flight control system. This means pilot commands are converted into electrical signals rather than mechanical movements. The computers constantly monitor aircraft speed, altitude, angle of attack, aircraft attitude. Using this data, the flight control system ensures the aircraft stays within safe operating limits. This system also provides flight envelope protection, preventing the aircraft from exceeding dangerous flight conditions. Fly-by-wire system flight envelope protection. Safety is extremely important in aviation. That's why the Boeing 787 does not rely on a single flight control computer. Instead, it uses multiple redundant computers working together. Each computer processes the same information and continuously checks the others. If one computer detects a fault in another system, it can automatically isolate the failed component. This redundancy ensures the aircraft remains fully controllable even if one system fails. Once the flight control computers receive pilot inputs, they calculate the best way to move the aircraft. Instead of moving just one control surface, the computers coordinate multiple surfaces simultaneously. For example, a turn may involve ailerons, spoilers, and rudder working together. This coordination improves aircraft stability, fuel efficiency, passenger comfort. The system ensures the aircraft responds smoothly and precisely to pilot commands. The flight control computers also support several automatic flight functions. These include autopilot operation, stability, augmentation, gust load alleviation. During turbulence, the system can automatically adjust control surfaces to reduce stress on the aircraft structure. This helps maintain a smoother ride for passengers and protects the aircraft from excessive loads. Flight control computers are not isolated systems. They constantly communicate with other aircraft systems, including air data systems, navigation systems, inertial reference systems. By combining data from these systems, the flight control computers maintain accurate aircraft control under all flight conditions. This integration makes the Boeing 787 one of the most technologically advanced aircraft ever built. The Boeing 787 flight control computers play a crucial role in modern aviation. By combining fly-by-wire technology, advanced sensors, and multiple layers of redundancy, they ensure safe, efficient, and precise aircraft control. These systems represent a major step forward in aircraft design, allowing pilots to operate complex aircraft with greater safety and reliability. Understanding these technologies helps us appreciate the incredible engineering behind modern aircraft. If you enjoyed this video, don't forget to like, subscribe, and follow Skyscience-Aircraft for more aviation engineering content.
Have you ever looked at the Boeing 787 cockpit and thought, why do its windows look so advanced and unique? The cockpit windows of the Boeing 787 are not just there for pilots to see outside, they are designed for visibility, strength, safety, and efficiency. In this video, let's explore what makes the B787 cockpit windows so special, how they are built, and why they are important for safe flight operations. At first glance, cockpit windows may seem like simple glass panels, but on the Boeing 787, they are actually a highly engineered part of the aircraft structure. These windows must withstand high-altitude pressure differences, extreme temperature changes, rain erosion, bird strike, impact, and even electrical heating loads. So, what looks simple from the outside is actually a very advanced multi-layer system. The Boeing 787 cockpit window system mainly includes two types of windows, the forward windshield panels and the side cockpit windows. The forward windshield gives pilots the primary forward view during takeoff, landing, and flight. The side windows improve lateral visibility, and also include features such as sliding or opening sections for operational and emergency purposes, depending on the design. Together, these windows provide the pilots with the visibility they need in all phases of flight. B787 cockpit windows are made with multiple layers, not a single sheet of glass. These layers are carefully designed to provide strength and protection. Typically, cockpit windows include structural plies, inner layers, and an outer surface that can resist environmental damage. This layered construction helps the window handle both mechanical stress and operational heating. If one layer is affected, the window still maintains overall integrity through the support of the other layers. One of the biggest challenges for any aircraft window is cabin pressurization. When the Boeing 787 climbs to cruising altitude, the outside air pressure becomes extremely low compared to the cabin pressure inside. That means cockpit windows must be strong enough to safely contain this pressure difference. The windshield is not only for visibility, it is also a load-bearing part of the pressurized cockpit structure. This is why cockpit window design is such a serious engineering task. During operation, cockpit windows face some of the harshest conditions in aviation. They may encounter heavy rain, ice crystals, dust, temperature shock, and in rare cases, bird strike events. That is why these windows go through strict certification testing. They are designed to remain reliable even when exposed to severe operational environments. This level of protection is essential because pilots depend on these windows during the most critical stages of flight. One of the most important features of the Boeing 787 cockpit windshield is electrical heating. Why is heating needed? Because at high altitude and in cold, moist conditions, ice or fogging can reduce visibility very quickly. Heated cockpit windows help prevent ice buildup, mist formation, and temperature-related distortion. They also help maintain clear forward vision in challenging weather conditions. Without proper heating, visibility could become a serious safety concern. Pilots need a clear view outside, especially during takeoff, approach, and landing. Even with advanced avionics and displays, direct visual reference remains extremely important. That is why cockpit windows must provide not only strength, but also optical clarity. The design must minimize distortion, reflections, and visibility issues. In aviation, even a small visual problem can become significant, so cockpit window quality is taken very seriously. Passenger windows and cockpit windows are not the same. Passenger windows are smaller and designed mainly for cabin use. Cockpit windows, on the other hand, are much more complex because they are directly involved in flight crew visibility, structural performance, and weather protection. They are larger, stronger, heated, and built to meet far more demanding operational requirements. So while both are windows, cockpit windows are in a completely different category. The side cockpit windows on aircraft are also very important. They improve side visibility for pilots during ground maneuvering and operational checks. They can also serve specific operational or emergency purposes depending on the aircraft design. The framing, sealing, and locking arrangement of these windows must be extremely reliable. A cockpit side window is not just an opening panel. It is a certified and carefully controlled aircraft component. From a maintenance point of view, cockpit windows require careful inspection. Engineers look for issues such as cracks, delamination, seal damage, heating faults, surface scratches, or discoloration. Even small defects can be important because they may affect visibility or long-term structural reliability. That is why aircraft maintenance manuals provide very specific limits and procedures for cockpit window inspection and replacement. Proper maintenance ensures the cockpit windows remain safe and effective throughout service. Because the windshield uses electrical heating, the system must also be protected and monitored. Aircraft systems are designed to control heating levels and ensure the windows operate within safe limits. This helps prevent overheating while still providing the necessary anti-ice and anti-fog performance. On a modern aircraft like the Boeing 787, system monitoring is an important part of keeping cockpit visibility reliable in all conditions. Think about a rainy takeoff or a foggy landing. In those moments, cockpit windows become one of the most important interfaces between the pilots and the outside world. They must remain clear, strong, and dependable. That is why Boeing designed the 787 cockpit window system to meet demanding performance standards. It is a perfect example of how aviation combines engineering, safety, and human factors into one component. The next time you see a Boeing 787, take a closer look at the cockpit windows. They may seem like a small part of the aircraft, but they do a huge job. They protect the flight crew, maintain visibility, resist pressure, survive harsh weather, and support safe operations on every flight. This is what makes the B787 cockpit windows far more than just glass. They are an essential part of modern aircraft design. If you enjoyed this video and want more aviation engineering content, don't forget to like, share, and subscribe. Let me know in the comments which Boeing 787 system you want explained next. See you in the next video.